Give me just 1 second. We're picking up in section 25. So last week we got through part of section 25 and kind of stopped there. So we'll finish 25, get into 26, and then finish it out. So yeah, here we go. Do you have any questions before we get started? Oh, hi, Trent. Starting with questions before we jump back into section 25. Okay, I think I'm going to sneeze. Yep, I did. Okay, so we're going to go ahead and jump in. We are in section 25, which is linear modeling. And we're going to start here in number 2 because we did number 1 last week. So if you remember, just a little bit of refresher. Oh my gosh, my tools are on the opposite side of normal today, so I could be lost. Linear modeling deals with the y equals mx plus b, where m is the slope and b is the y-intercept, and the x and y that you see in the formula represent all ordered pairs that fall on that line. So we are going to take the information given to us in this one sentence and then create a linear model out of it. That is our goal. So the first things first, the population of a town in 1970 was 5,600, and in 1995 it was 4,100. So when you think about an ordered or a linear model, right, thinking about letter C, we want to create a linear model, we need a slope and a y-intercept. So we need to think about how do we find those two pieces. Well, before we really jump into finding our slope, because generally we do that first, I don't know why, we just do, I want you to refresh on the y-intercept. The y-intercept is where the graph crosses, the y-axis. So any graph that we have, it's where it crosses the y-axis, meaning the x value has to be 0. Well, when you look at the information they give you, 1970 was 5,600, and in 1995 was 4,100. If we write our ordered pairs with this information as it's given, well, we would say 1970 was 5,600. We always use time as our x value because time is independent. And we would have 1995 as 4,100. But if you look at that, neither x value has a value of 0, and therefore we don't have a y-intercept. So we will be unable to write a linear model with ordered pairs the way they're written. So we play like this what-if game. We say, okay, 1970 is our earliest year. So let's pretend that in 1970, our x value is 0. So that changes that ordered pair to be 0, 5,600. And then do just a little bit of math. Well, let's just say you were born in 1970, right, because that's when you're 0, in 1995, how old would you be? Or how many years have passed between 1970 and 1995? Well, all you gotta do is subtract those 2 years to find out x would have a value of 25. So my other ordered pair would be 25, 4,100. And by doing this, we now have an x value of 0, so I know that 5,600 is my y-intercept, because that is the y value when x is 0. So it is important to make sure that when you're doing your ordered pairs, one of them has an x value of 0 because you need a y-intercept. Now we have ordered pairs, we can go ahead and find our slope. So remember, slope, y2 minus y1 over x2 minus x1. The little numbers just represent ordered pairs. You want to make sure the ordered pairs are right on top of each other. So if I go ahead and do that, we'll just call it 4,100 is my first y value, right? So here's y2. I'm going to subtract 5,600. And then I'm going to divide 25 minus 0. I'm going to let you guys kind of catch up, do a little math. I know I'm kind of writing all over the place today. Stop me if you have questions. I'm going to let you go ahead and simplify that. Let me know what you get for a slope when you simplify that blue fraction. Negative 60. Exactly. So our slope is negative 60. Now that I have a slope and a y-intercept, now I can go ahead and put those together to create a linear model here in letter C. I'm going to change it back to yellow. So we always start with y equals slope, which is negative 60, times x plus my y-intercept of 5,600. So now we can use this linear model to predict populations of any years. Any years. So if we go ahead and look at that, right, so that's letter D, we're going to use this model now to predict for 2017. Well, if you think about it, it goes back over here. Okay, 1970 was x equals 0. So now we're talking about 2017. How many years later is 2017 when compared to 1970? Any idea what our x value would be? 47 is correct because it's 47 years later. So our x value, right, plug it into our model. So y equals negative 60 times 47 plus 5,600. So it becomes an order of operations, right? You're doing this multiplication piece first, then you add. So we would have approximately 2,780 people in the year 2017 based off of this information. Okay. Any questions here on, I guess, number 2? Oh, okay. I want to do one more from this section. There we go. And I would like you guys to try this one. It's basically the same thing. So the state of Indiana has set a goal of 60% degree attainment among adult Hoosiers by the year 2025. So here's the year, here's the data. And then you get the other piece from part A. If the percentage of Hoosier adults with degrees was 33% in 2010, construct a linear model. So I want you to go ahead and just try this, number 3A. Just kind of, so you're going to have to do your y-intercept, your slope, just like we did in number 2. And then once we make sure that we have the model correct, we'll go ahead and go to part B. But I want you to go ahead and try that on your own first. Okay, how we doing? We know we need a slope and a y-intercept. Can anybody give me either of those at this point? Yes, the y-intercept is 33.2 because when you're looking at your ordered pairs, 2010 is the earliest year. So x is going to be 0 for the year 2010. So there's 0, 33.2. Yep. So this other one, so 2025 would be an x equals 15. So that would give the other ordered pair 1560. Yep. So far, so good. Then you use those ordered pairs in order to find your slope. So I'm going to use a different color. I don't know where this paper is that has this answer on it. So yes, 1.79 is the correct slope. Did everybody else get that? Okay. Kara's given us the answers, but we're dealing with, right, y value minus y value over x value minus x value. So 26.8 over 15. If you divide that, you get 1.79. So that gives you the model, y equals 1.79x plus 33.2. So now let's go ahead and go to part B. We're talking about the year 2016. So you say, okay, over here, how does 2016 compare to 2010? Well, it's 6 years later, so x is 6. So if I plug 6 in for x, 1.79 times 6 plus 33.2, what would we predict? Hey, and excellent job with the percent. Yeah, so we would guess that in the year 2016, 43.94% of Hoosier adults would have a degree, right? That's what this says. Excellent. And this would be a predicted value. When you use the linear model, that's predicted. Actual and predicted are usually, well, they can be close. They don't have to be, but very rarely are they going to be spot on. So just kind of keep that in mind. Okay. All right. Any questions about finding slope, y-intercept, using a linear model, any of that? Anything there? Okay. If you think of a question later, that's totally fine. But we are going to move on to section 26, which is scatter plots. This section is very short, so I kind of want to just keep you in mind here. So scatter plots are basically, there's dots all over the place. Okay, and a scatter plot is great, right? That's real life data, because real life data is all over the place. It's not going to be nice and linear. It's going to be all over, because that's how life is. It's random. So in the real world, we have a scatter plot, and then we have what we call a trend line. And a trend line, or a regression line, or a line of best fit, all kinds of things. A trend line kind of cuts right through all of the dots. And the trend line allows you to talk about the predicted values, right? Because this is a line, so we would use the y equals mx plus b to create a linear model to talk about this line. Now, the trend line, it's really difficult to do this by hand, like on pencil and paper. Excel is fabulous with this. And with that being said, you do have a trend line activity in Excel to do, and I will be posting an Excel help video to go with that. So as usual, when after I take this video and put it into a watchable format, I will post that in the announcements, and I will post that Excel help video. So if you've never created a scatter plot and a trend line in Excel before, that video will walk you through. It's short, and it will walk you through how to do that. So here's the purpose of all of this, right? So we have the scatter plot, right, the pink dots. We have the trend line, which is orange, cutting through, and it shows us that we can model our data linearly with that line. Well, how great of a prediction is that line? Sometimes, you can throw a line through data and it means nothing. And there are times where the line might be fairly accurate. And so we get to our second term here, which is the linear correlation coefficient, which is noted by the letter R. So just like slope is M, y-intercept is B, the linear correlation coefficient is R. The purpose of this is to show how good of a fit that line is. Meaning, so R can be anywhere from -1 to +1. Okay, so the sign of R, whether it's positive or negative, will depend on the sign of the slope. So in my particular orange line here, I would have a positive slope, right? It's going to be positive because the line goes up. So if this was the case, my R value would also be positive because the slope goes up. So we would have an R value somewhere between 0 and 1 because it's got a positive slope. If your R value is exactly 1, that means your dots fall in an exact straight line. right? Like I'm putting in now. So if you have exactly a straight line, your R value is 1 because it's exactly linear. With my pink dots all over the place, the R value that goes with my orange line would probably be closer to, I don't know, maybe 0.78. I'm just making this up, but it won't be too far away from 1 because it is showing a positive linear motion, but it's not exactly linear. If we had dots that go this way, I know those are not very good dots, but you guys are used to me by now, so you're with this. And we throw a line through it, that dark green line that's hard to see. That gives us a negative, right? So here we would have a negative slope. And if we have a negative slope, that means we have a negative R value. And those dots are very close to my line, so maybe R would be something like negative 0.92, all right? And now I know what you're thinking. You're like, how am I supposed to know what R is by looking? Well, you don't. Okay, so, and this is not something you're ever going to do by hand. This is something that Excel is going to help you with. So when you put a trend line in Excel, it will give you two things. I want to go to the next page. When you're in Excel, the trend line is going to do two things. Okay, so let me get a, again, here's my scatter plot. Here is my trend line. And then you can hit a button in Excel and it will spit out y equals 0.34x plus 7. And then it will say r squared equals 0.84, whatever, okay? So it will give you your model, y equals mx plus b. So I know that my slope is 0.34. I know my y-intercept is 7. And then it will tell you an r squared value. Well, if you recall, the linear correlation coefficient is not r, or it's not r squared, it's r. So to find linear correlation coefficient, you're given r squared is 0.84. How can I go from r squared to r? Does anybody have any idea mathematically how to go from r squared to r? Square root is absolutely correct because you're unsquaring something. So if I square root both sides, and I'm making this up as I go, so the square root of 0.84 would give us 0.9165. And you would want to round to whatever it tells you to round to, right? So 0.9165. Great. That's pretty close to 1. So we would say there is a strong, positive linear correlation between whatever variables we're talking about. And that's the whole point of R, is that it tells us whether or not that there's a strong correlation between the two variables, right? Whatever is on the x-axis and the y-axis. So the closer your R value is to 1, the stronger the correlation is. The two things are actually related mathematically. If it's not very close to 1, well, then they're not very closely related. Now, one thing that I want to mention, your calculator is always going to spit out a positive value for R. You need to make sure that the sign, right, the symbol, whether it's positive or negative, matches the symbol of your slope. So in this example that I just threw up on here, my slope is positive, right? My line goes up, slope is positive, and therefore my R value is going to be positive. So you have to make sure those two match. If I had drawn the line like this with a negative slope, but the same R value, then R would be a negative 0.9165. So you have to make sure that you're careful and paying attention to the signs of your slope and your y-intercept, or your slope and your linear correlation coefficient. Okay, but the only new thing in section 26 really is the linear correlation coefficient and playing with Excel. However, because of web work, I want to throw one more thing out. Okay, a lot of times years are going to be on the horizontal axis, right? These are the x values. Now, we just did two examples where you said x is 0 for 1970 and blah, blah, blah. Well, if this is the stuff that you have and we have ourselves an equation, And the question says, estimate for the year 1992. You have to pay attention, right? Use the skills of observation. Look at your X values here. These X values are actually years. If they show actual years, then you're going to use actual years for X. So in this example that I have on the screen right now, if I wanted to estimate for the year 1992, I'm going to use an X value of 1992 because that's what the X values are representing. Okay? It's very different than if it starts at 0 and goes to 10, 20, 30. If the green now is what we're dealing with, and you wanted 1992, well, then you would use X as 22 because 1992 is 22 years after 1970. So it's all about paying attention, looking at your X values and seeing what you're given. Not every problem is done the same way. You have to see what your X values, how are they represented, and that's how you will use your X values. All right, that's the biggest issue people have in section 26 is that they don't pay attention to the X-axis. They just want to do every problem the same way, and you can't do that. You have to really let your logic and your common sense come in, and you have to pay attention to the way that they are actually labeling the X-axis, if that makes any sense. All right, who has questions on section 26? Because that's all I'm doing for that one. Again, I will post a video about Excel with trend lines and scatter plots. Okay, if there are no questions on that section. And again, there are videos to go through the packet for each of these sections. So if you want, more work with that, which is always recommended, right? Because I just this is the big picture. You really may want to go back and watch a few of those videos. Okay, the last two sections of the packet, right? This is it. Next 30 minutes, this is all we got. We're going to deal with exponential growth and decay. So section 27 is growth, right? Growth goes up. Section 28 is decay. Decay goes down. There's the big difference between section 27 and 28. So I just kind of wrap them together. Now, when we get to the formula for exponential growth, and this, is on your formula sheet. A stands for your ending amount. And then we have A sub 0, which is the initial amount, right? So it's kind of like, if you think about compound interest, this is very similar to compound interest. So your ending amount equals your initial amount times your growth factor raised to your time period, whatever that might be. And in my experience of teaching these sections, exponential growth and decay always go a lot easier than linear modeling. So don't let this initial formula freak you out because really it's not that bad at all. So there are two ways to find this growth factor. One is to take 1 plus the percent increase. So, again, think about compound interest. If you had a 4% interest rate, well, that's a growth. So 1 plus 4%, very similar to that formula. And depending on the way they give you the data, you also can think a new value divided by the subsequent old value. So depending on how they give it to you, and I will show you that in our first example, how you can use either one of those. Actually, I want to throw in a third way. If they say something is doubling, well, if you think about it, doubling means multiply by 2. If it's doubling, your growth factor is 2. If they say something is tripling or triples, well, triple means to multiply by 3, so your growth factor would be 3. So that would just be giving you that information and not necessarily making you find it. So, okay. Also, I would like to remind you that percent increase, that's relative change. Back from sections 23 and 24, when we did absolute and relative change was also percent change. So if it's a positive relative change, that is percent increase, right? It's all the same. So all of these last couple sections really are interconnected. But this is the formula that we're going to be playing with here for the next 20, 25 minutes or so. Okay, so there's your basic intro. Let's go ahead. Oh, we've already talked about the growth factor. So let's go ahead and get to this problem. We're going to do this table kind of together, but kind of not. in terms of, I'm going to help you out because we don't have a ton of time. We can't find the absolute and relative change for this first piece because we have no old value. Remember that absolute change is new minus old, and relative change is new minus old divided by old. Just that's back from sections 23 and 24. So when we look to find the absolute change for week 1, that means that week 1 would be new and week 0 would be old. You're always using the year, the week before. Okay, so absolute change, we would take 14 minus 10. So the absolute change would be 4. And then we would take the new minus old, which is 4, and we would divide it by the old value, which is 10. And I get 0.4. Right? Now, when you move on to the next week, week 2, now week 2 is new. That makes week 1 old, right? So every time you just kind of move by one section. Okay, go ahead and finish the table, right? Those 4 pieces. Hopefully it's not too bad. Give me a yes in the chat box when you're ready. Okay, so if we look at the absolute change for the next 2, we have 5.6 and 7.84. Our relative change is 0.4 for all of them. Now, when you're looking at these and you're trying to pay attention and you're checking this all out, absolute change is a number, right? A number thing. If you have a constant change, which would be this, you would have slope, right? Because slope is a constant change. Well, this is not constant. 4, 5.6, 7.84, those are all different. So I do not have a linear model because I do not have a constant change. That's how we can tell by looking at this table. But when you look at the relative change, this is a constant rate. And we know that relative change is the same as percent change, and therefore I know that I have an exponential model. Okay, so that's part B. What's the same? Well, relative change is the same. Relative change is percent change, therefore I have an exponential model. Okay, how do I find the growth factor based off of this information? Anybody have any ideas? Remember, the growth factor can be found by taking 1 plus the percent increase. So, and Kara, we're going to do that one next. Yeah, I'm going to do it both ways. So one way is to take 1 plus the percent increase is 0.4. Right, it would be 40%, but we don't play with percents, we play as decimals. So we can add those two and we can get 1.4. As Kara mentioned in the chat box, which is fabulous, we can take new divided by old. So if you it's any two of these values, let's just take these two. They've got to be consecutive. 14 would be new and 10 would be old. So we would take 14 divided by 10. And again, you would get 1.4. And that would work no matter which two of these values you took, as long as they were continuous. They've got to be right in a row. Then it works. Okay, so since we have our growth factor, now we can find a model. We can write our exponential model. So our ending amount equals our beginning amount. How much did we start with in this particular problem? 10, exactly, because the starting amount is still when x is 0. So I start with 10. Inside my parentheses is my growth factor, and then I raise it to my time period. And in this problem, my time period is number of weeks, right? Because that's what x represent, and that's weeks. Okay, so now that I have that model, I can use this to predict for week 6. Because I would say, well, if I'm predicting for week 6, that means my time is 6. So A equals 10 times 1.4 raised to the 6th power. What do you get if you put 6 in for t? This goes back to the compound interest type stuff. I did not get 70.3. Doesn't mean I'm right. Try that again. I got 75.3. Did you have a typo? Okay, good. Scared me. Yeah, so we're talking about money here, so this would be $75.30 based off this information. Okay. All right, so Trent just took off. That's okay. Jacob, you doing okay? All right, so that's kind of the process of working through one of these. Let's do a problem that's not table related. Let's just do one given some information. So frogs increase at a rate of 32% every week. If there are currently 40 frogs around my pond, let's write a model and let's estimate how many frogs we'll have after 10 minutes. So, okay, I want you guys to try this one. Give me a yes in the chat box when you're ready to talk about it, but give me a model and estimate frogs after 10 weeks. All right, how's it going? Think about the two pieces that you really need to write a model. We're going to need a percent, in this case, a percent increase because they tell you it increases, which leads us to our growth factor, and we need an initial amount. Those are the two pieces that you need to write an exponential model: growth factor and initial amount. So our ending amount, and if you wanted to use y because you like y better than a, that totally is okay. But what is our initial amount in this problem? How much do we start? We start with 40. All right, what's going to go inside my parentheses here? 1.32, very good. And then I have my time period. In this case, my time period is weeks. Just to, it's always important to just highlight that, make sure you're aware. All right, then we get to part B, how many frogs will I have after 10 weeks? What do we do with that 10? We throw it into the variable for t. So A equals 40 times 1.32 raised to the 10th power. And how many frogs are we going to have? Very good. So roughly 642 of them. That's a lot of frogs. Too many. Yes, that's a good answer. Good answer. Okay, that essentially is section 27, right? Exponential growth. So now we're going to go into exponential decay. So here's the difference in formulas. Ending amount equals initial amount. In here we have a decay factor raised to the t. So there's the difference in formulas, is that instead of a growth factor, we have a decay factor. And the decay factor is found by taking 1 minus the percent decrease. Makes sense. If you're decaying, you're getting smaller. And again, remember, this is a relative change. So if your relative change is negative, you have decay, and you go from there. Okay, so let's go to, got another, wrong button. There we go. Got another table, because why not? Again, we can't find this one. Okay. I would like you guys to try, fill out this table, absolute change, relative change, very much like the table we did last time, but we have different values. And obviously you can see your values are decreasing. So this is a good review on absolute and relative change again, because the test is next week, so that's important too. Yeah, okay, fill out the table, give me a yes, or else I'll check back here in about 2 minutes, and we'll go from there. There we go. So when you look at your absolute change, you can see that they are inconsistent, right? We do not have constant change, therefore we do not have a linear model. So these, they're not, so we have no linear because we do not have constant change. Okay, relative change. What did you find when you looked at your relative change for each of these? Negative 0.2, exactly. So all of these are negative 0.2. You know, and that would be a negative 20% if you want, excuse me, if you wanted to look at it as a percentage. Jacob, where did you get 0.8? Are you working ahead? Maybe? But for this column, you should have gotten negative 0.2 in this column. Right? So if the relative change is the same, that means we have, what is the same? The relative change, and what does that mean? That means exponential. Right? So because it's negative, we know we have exponential decay. So to define our decay factor, we take 1 minus the 0.2, right? Because there's the negative 0.2, you can see that. And that gives us 0.8. So our decay factor is going to be 0.8. That's what will go inside the parentheses. So that gives us a model of ending amount equals, how much did we start with? 120. Then we take our decay factor of 0.8 and we raise it to our time period. So the well, relative change, Jacob, answering your question. So remember, new minus old divided by old. So if we're looking at this spot right here, using these values, this one is new and this one is old. So we would take 96 minus 120 divided by 120, which would simplify to be negative 24 divided by 120. And that's how we get relative change, based off of sections 23 and 24. Now, if you wanted to go, oh, there you go. If you want to go straight to the decay factor, remember, the decay factor is a lot like the growth factor, and you could take new divided by old. So if we would just take the 96 divided by 120, that would give you 0.8. So you could have just gone straight to the new divided by old in order to get the decay factor if you didn't want to do the 1 minus the percent decrease, right? That's up to you entirely. Other questions on this one? I just like this because it ties in absolute relative change, gives us a little refresher on that. And it is important to recognize, absolute change, if those were all the same, that would be a linear model and that would be our slope. But in this case, we're in the exponential section, so that's really what we're working on. All right. So then in letter D, if it talks about 6 weeks, well, we would just say, okay, that means T is 6. So A equals 120 times 0.8 raised to the 6th power. And how much is left after 6 weeks? $31.46 is correct. Very good. Very good. Okay, questions on that problem? All right. I think I only have maybe one. Yeah, okay. All right, so let's try one without a table. An SUV depreciates 8% a year. If you buy a $26,000 SUV, let's start with a model to show this, and then how much is it worth after 5 years? Okay, so try this one, a model, and then how much is it worth after 5 years? Okay, so A equals initial amount. What do we start with? 26,000. All right, what's going to go inside the parentheses? 0.92. Very good. Depreciates means it decays. So we're going to take 1 minus the 8%, which is 0.08. That gives us the 0.92. We raise it to the t power. So there is our model. Then in part 2, we want 5 years. So 26,000, 0.92 raised to the 5th power. How much is your car worth, well, SUV, excuse me, after 5 years? $17,136.12 is correct. Good job, both of you. Good job. All right, so that's what I got. That's the end. We have about 8 minutes left. If you have any other questions, have you both signed up for a time for the exam for next week? Because remember, every online class in all disciplines are taking finals next week, so the space is going to be a little bit more difficult to get into than what we've been in the past. So if you have not signed up for a time yet, please do so. So good job for those of you that have. It's great. So we have that coming up. Very good, very good. You have the last project is due at some point. Let me grab my paper. I didn't make a slide this time of when everything was due. So what we have left, we've got project 3 that's left. 4 sections in web work, right? 25, 26, 27, and 28. You have an Excel trendline activity, a couple discussion boards, 2 quizzes, and then the last exam. So be careful. I'm going to hopefully catch up on grading everything that was due yesterday, today. That is my goal, so that you really have an idea of where you're at. If you have any questions, please get those to me. I will be posting the Trendline Excel Help video, as I mentioned earlier. So if you need that, you can find that one. But other than that, next week, I will be available normal time, 2 o'clock on Tuesday, but it's just a question answer time. So if you're working on preparing for the exam and you have questions, you can email them to me ahead of time so I can prepare, have them typed out, or you can just, verbalize them or put them in the chat box during class time. Either one of those is fine. And if you don't have any questions, then, go do your thing. And I will be grading the exams kind of as they come in next week. So you should have, as soon as everybody has taken the final exam, I will officially post final grades. But the grades will be kind of finalized in Ivy Learn as you take the exam. So I will go behind you and kind of grade them as soon as possible, because I know people want to know where they fall. So just kind of keeping you updated on that. I'm going to start grading projects this week as well. So if you turn in project 3, the turnaround of the grading of that will be quite a bit quicker than projects 1 or 2. So any other questions from anyone before we sign off for today? All right. Have a great week. I'll talk to you next week if you need me. If not, it's been a pleasure, and I wish you both well. And yeah, let me know if you need me. Thanks, guys.